Hello friends, this is Anand Pai from Academy in Pursuit of Engineering Excellence. Today we will continue our series on fluid mechanics, in that chapter 1 properties of fluids, and in that surface tension. Now as we know, surface tension we encounter a lot in our day-to-day life. Like if we drop a pin in water, this pin can float on the surface of water, okay, or a liquid droplet, a water droplet will move freely or roll down freely on the surface of a hydrophobic leaf. Most of the leaves are hydrophobic. Also, an ant who is otherwise very strong in the sense it can lift 50 times its own weight, but it struggles a lot to come out of the water. See here, there is an ant which is trying to come out of water. It struggles a lot. You can see that for yourself. Okay. Now what is that which causes this surface tension? Now the thing which causes the surface tension is the way the liquid is. Now when we say the liquid, what differentiates liquid from gas? The thing which differentiates liquid from gases is its cohesive nature. Liquid molecules wants to be together in general, unless and otherwise some other friends come which they like a lot. Now when you say cohesion is attraction between like molecules. When we say adhesion means attraction between unlike molecules. Now if you observe here, this I will say this is these spheres or circles represent the molecule of a liquid. Now say here there is some other gas. Okay, we will now for our ease we will consider this as water molecules and there is air above. Now water molecules have higher cohesive forces with itself. It is cohesion is more with its own molecule compared to the adhesion with the air molecules. Now let us consider a molecule which is inside the bulk of the liquid. Now the molecule which is inside the bulk of the liquid will be attracted from all the directions by the nearby water molecules. But think of a water molecule which is near the surface. Now the water molecule which is near the surface, it has attraction only from inside the bulk inside and from the sides. Here the forces are very less because it is air which is here. Now air does not pull this water molecule as much as the surface molecule which is inside. So now this creates a scenario where you see this particular thing happens. This molecule which is there is being pulled lesser by air but pulled with a higher force by the molecule which is inside, as well as there is similar force by the nearby molecule. So what will happen when this is pulled this side? There is a tension along this line. Are you getting that point? There is a tension along this line, and this tension we can say it is surface tension. Now we can say that surface tension is an interplay between adhesive and cohesive forces. Now we will consider one of the effects of surface tension is forming of the meniscus in a container which is holding the liquid. Now consider this to be a glass container. These both two containers are glass containers, and here in the first container water is put and the second container mercury is put. Now if you see the container in which water is put, the water forms a concave meniscus and this mercury forms a convex meniscus. This happens because of the interplay between cohesive and adhesive forces. The water molecules has more adhesion towards glass than cohesion with its own molecules. That's why this water molecules want to be close to glass rather than its own types. Okay, so what happens, it climbs over the glass surface, whereas this mercury doesn't have any liking towards glass, it has more liking towards its own molecules. So what happens, it comes near, it tries to go away from glass as much as possible, and that is the reason it has a convex surface. Surface tension can also be interpreted as the energy required to create new interfaces or new surface of liquids. Now how do we understand this? let us consider a C-shaped rod and another rod which is supporting a soap film in between this. Okay. Now, if you extend this soap film, you require a force to extend this by a small length L. If you remove this force, it will go back to this particular position. Okay. So, to create this new extra surface, I have supplied some energy to this soap film. That energy is equal to force into the distance delta L. So, energy per unit area is F into delta L. So, now this F into delta L, if you see the units, unit is force is Newton, M is meter per meter square. So, what happens? This is joules per meter square, that is the energy required to create a new surface. As well as if you cut M and M, you will see it is Newton per meter, which is the unit of surface tension. Now, the surface tension is always represented in terms of Newton per meter or joules per meter square. Now, this representation we have understood. We have understood in terms of creation of new surface. But this representation, Newton per meter, force required per meter, we will try to understand how is this force required per meter. Let us understand like this. Now, this force, how is this force? We will understand again here. Now, this force required is per this meter, the length of this soap film, that is very important here. Okay. This length from this red color rod which is there, the length of this is what is meter. Okay. So, Newton, what is the force required for 1 meter of this surface? Okay. What is the force required to move this 1 meter of surface is what is the surface tension is. Now, let us understand this in terms of forces. Now, here if we see, if this is a liquid vapor interface, this is a liquid vapor interface which I have put here. Now, the surface tension force is per unit this length and the force is there in this direction. Now, this is something difficult to understand, is it not? Let us understand this with some other examples. Now, let us understand this particular one, capillary action. Okay. Now, if you see the capillary action, because of surface tension force, the adhesive forces, what happens? This liquid column climbs inside this capillary tube. Now, if you see here, this is a surface. If you consider this line, and the equivalent to this line would be the circumferential line here. Now, you see which is the direction in which it is going. This is the direction in which the force is there, which corresponds to this direction. Are you observing this? And here this theta is the angle between this and this, which is called the contact angle. Okay. Now, the contact angle for a glass with water is generally acute angle. Okay. Now, let us understand this again. See, Newton per meter length, that is the cause of surface tension. That is how surface tension is also measured. Surface tension is measured by pulling out one sheet from water surface, and we will see what is the force which is required. So, the similar thing, Newton the force required to pull 1 meter of a surface. 1 Newton, how many newtons required to pull 1 meter? That is surface tension. Okay. So, now if you see the capillary action here, now the capillary action here, you see the force, this particular water column is in equilibrium under forces. One is the surface tension force, another one is the gravity force. Now, what is the gravity force here? Gravity is rho g, the weight density, into height, this height, into the area of this pi d square by 4, and that is equalized by pi d around this, where the liquid, gas and the adhesive surface is in contact. So, that is pi d is the length of that, sigma is the surface tension force in this direction, and the component of that in this vertical direction is cos theta. So, the capillary rise, the height to which the water column rises is equal to 4 sigma cos theta by rho g d. Now, in case this was a mercury column, okay, then this theta would be obtuse and there would be a capillary fall instead of capillary rise. Now, this surface tension causes some more effects. One of the effect that is caused by a free surface of a liquid enclosing itself is the increase in the pressure inside. Okay, this happens when the free surface encloses some matter inside it. Okay, one of the examples or some of the examples are droplet, bubble and liquid jet. Okay, now if you consider a droplet and we take a equatorial section here, okay, the forces over the sections are this way. One is surface tension force on its circumference and the pressure forces in the middle. Okay, and these two counteract each other to keep the droplet in equilibrium, and the pressure here will be equal to 4 sigma by d. Whereas for a bubble, when we see, there are two surfaces, one is inside surface and one is outside surface. So that is the reason we have 2 into pi d sigma is equal to p pi d square by 4, where p is the pressure. Now the pressure P is equal to 8 sigma by d. So the pressure inside a bubble is much larger than that of the liquid droplet. Okay, similar thing happens with the liquid jet. Inside a liquid jet, if you consider it as a cylinder, now it will have surface tension on its circumference, and from the bulk of the liquid, the section, you have the pressure here, and the surface tension force is 2 into L, the length, into 2 into d, the diameter, into sigma, is equal to pressure into the area, which is L into d. Now if you consider diameter, for the cylinder, if it's very big, the diameter is much more negligible than it is negligible compared to the length. Okay, for the negligible diameter, we can say it is 2L into sigma, and L cancels over here, and P is equal to 2 sigma by d. Okay, so let us summarize whatever we have done. Okay, so we have seen surface tension is caused by the interplay between adhesive and cohesive forces. Surface tension is equal to the energy required to create new liquid gas interface, like we have seen with the soap film. Okay, surface tension is responsible for creation of droplets and bubbles. Also, surface tension is responsible for capillary action, either capillary rise or capillary fall. Okay, I hope you have learned something new here. I request you to kindly subscribe for this channel. Also press on the bell icon so that you can get new notifications. I am going to complete fluid mechanics, and this particular videos will be helpful for competitive exams also. Okay, so best of luck. Thank you very much.